It's my great pleasure to talk at the summer school. Here, I'm actually giving some more like philosophical overview of the Euler equation from a Lagrangian point of view. And so let's see what we can do from here. So let me start with a very simple setting of the Euler equation. This is incompressible Euler equation on a fixed domain first. So on a fixed domain, the Euler equation takes the form which has been discussed in the last few days. And on the boundary, we take the non-slip boundary condition. And so it's on a finite domain. And then because of these conditions, we take the Sobolev space as the working space. Here, we consider vector field with divergence precondition and also with the non-slip boundary condition. So the vector field on the boundary, they are all tangent to the boundary. And so that means that the particles can slip on the boundary because there is no viscosity, but they cannot really penetrate the boundary. The boundary is considered as rigid. And the first issue we're going to start to consider is the structure near steady states, steady flows. So steady state, of course, satisfying this equation. Then there is no evolution here. There are many examples of steady states. For example, in the 2 dimensions or higher dimensions, one can consider channel flow with shear flow. Shear flows in the channel flow are steady states. So in these cases, the flows are in one direction, but the speed depends on the height or other coordinates. If in 3D, then here it can depend on other coordinate if this is only the first component. And in the 2 dimensions on a bounded domain or on a domain, it is well known that steady state can be found by solving some semilinear elliptic equation. So we're not going too much into that. But one thing is that given a steady state, it might be a shear flow or something else. Then what do we know about the structure, local structure near the steady state? For example, do we have the stability, instability at the linear and the nonlinear level? So that's like a very basic question. So usually to address these questions, for example, the instability or stability, the first step is to linearize the Euler equation at the steady state. So when the Euler equation is linearized as a steady state, we get the linearized equation. Here, we call this linear operator L. So if we look at this operator, we see that here, this is basically a transport by the steady flow. And this is a bounded operator on the vector field V. And here there is the pressure, the linearized pressure term. If we believe that the linearized pressure term is a nice term, which it is, then this is a bounded perturbation or nice perturbation to the transport operator. And the transport operator is reasonably nice. So we can say that the linearized equation can be easily solved as a PDE. And but at the same time, when this equation can be solved, but the transport part does not really have anything more than solvability. It gives you, in the language of the semigroup, it gives you a strongly continuous semigroup, but it does not provide any smoothing. So it has it's not an analytic semigroup in that language. So if we want to study the spectrum of this operator, then we will see that the spectrum actually depends on the function space we choose. Or the linear stability will depend on the function space we choose. Here there is the K here. So let me take a very simple example to demonstrate how the dependence on the space we choose. This does not really happen too often in semilinear equations like nonlinear wave equation or nonlinear Schrödinger equation. Here, I'm taking a simple example of the Couette flow. It's probably less illustrative compared to some other flows, but it's easier to present. So the Couette flow in 2D is a shear flow with a linear shear. It's actually a pretty degenerate case because in the Rayleigh theorem, it says that the instability happens. The necessary condition for the instability to happen is the shear should have an inflection value. Here, it's completely linear. So if we linearize the Euler equation around the Couette flow, you get this linearized equation. Okay, this linearized equation is probably not the best equation to look at. Then it's easier for this particular case, or in many two-dimensional problems, it's easier to use the vorticity formulation. So if one change that to the vorticity formulation and look at the linearized Euler equation, so you linearize the Euler equation in the vorticity transport. In the vorticity formulation is basically a transport equation, transport of the vorticity by the velocity field. So if you linearize, you simply get the transport of the vorticity at the Couette flow. Okay, so there is no more term like the vorticity of the shear then times the derivative of the linearized, then times the linearized velocity field, because the Couette flow has a linear shear. So it's a very simple equation. You can write down the solution right away. So omega 0 is the initial vorticity. So everything can be written down extremely straightforward. And then you see that in this simple example, the linearized vorticity is simply transported by the Couette flow. And this transport is, of course, volume preserving. And then immediately you can get most of the properties of the linearized Euler equation as the Couette flow explicitly. So one thing one can see is that because the vorticity, the linearized vorticity is transported by a volume preserving Couette flow, then you see all the LP norms are conserved. So this is a strong indication of stability. And not only that, you can also check, study the spectrum of the problem. Then it's very easy to see that the spectrum of this operator is the whole imaginary axis. So from the spectral point of view, this is spectrally stable. Here I'm taking, say, the L2 space, for example. Then it's spectrally stable. And also it preserves all the LP norms. So all of these are strong indication of linear stability. And not only that, it has a stronger property than just the usual linear stability. For example, if you take the initial vorticity without the shear component, so if you do the Fourier series decomposition of the initial vorticity, assume that the zeroth mode is vanishes, so there's no shear component. Then in this case, you can see that then the corresponding vorticity, the linearized vorticity, will converge to 0 in the L2 norm. So there is some asymptotic stability here. And if you assume a little bit more of the regularity of the initial vorticity in the vertical variable, then you see that the velocity field, the linearized velocity field, will converge with a rate, like 1/t. If you assume a little bit more of the regularity of the initial vorticity in y, in the vertical coordinate, then the second component of the velocity converge like 1/t squared. Okay, we cannot increase the regularity more to get a better decay. Here, there are many reasons. But the point is that here, you see, the Euler equation has no a priori dissipation or dissipative mechanism involved. But in the linearized problem at the Couette flow, we do see some of the decay here. So this is usually referred to as invasive damping. This also happens in other problems, like in the Vlasov-Poisson system. Then there is a famous Landau damping. That is also another example of decay of some quantity in the Vlasov-Poisson case. That's the electrical field. The decay of some quantity when the system does not have a priori dissipative mechanism. So all of this indicate that the Couette flow should be considered as linearly stable. Okay, but on the other hand, if we change the space from LP space or L2 space to some Sobolev space with better regularity, HS with S bigger than 1, then immediately from the explicit form of the solution, we can see that the vorticity, the velocity actually has a growth in T, and algebraic growth in T with the exponent S minus 1. So in this sense, the system should be considered as linearly unstable. Okay, it's not exponentially unstable, but it's unstable. So here we see the impact of the space we choose actually has the regularity of the function space we work on has some impact on the stability issue. Okay, the reason you may think is that because some more and more small scales are created and the growth happens in the small scales, but not in the larger scale. So you don't see the growth in the LP norm or L2 norm, which probably put more weight on the long wavelengths. And when you go to the Sobolev space with higher regularity, then more weight are put on the small scales, and then you see the growth over there. So, but physically, it is more interesting to focus on the growth in the long wavelengths. I talked about the specific example of the Couette flow, which is very explicit. In general, if you linearize the Euler equation around a steady state, and so in general, it happens very often is that the spectrum of the linearized equation has some point spectrum, there are eigenvalues. And there are some, then there is a set of the essential spectrum. And usually they live in a vertical band in the complex plane. And the eigenvalues are, of course, nice. Then they are independent of the choice of your space, of course, because you have eigenfunctions. As long as you don't choose a function space which is too smooth to exclude the eigenfunctions, then the eigenfunctions are always there if you change the space. So the eigenvalues are independent of the choice of the function space. But however, if we change the function space, then the essential spectrum distribution might change. More specifically, this depends on mainly two things. One is the Lyapunov exponent of the steady flow, which we call the V star somewhere. So that Lyapunov exponent has a great impact on the width of the essential spectrum band. And also this exponent, the index, the regularity index also has something to do with the width of the essential spectrum. Okay, and then when we see this picture, then it's very, if we have a steady state where the linearized equation does have this distribution of the spectrum, then immediately we can imagine that there should be some growth, exponential growth induced by the linear equation. So in that case, we can see the exponential growth coming from the eigenvalues and also probably from the essential spectrum. But the growth in the essential spectrum, just like in the Couette flow case, they are mainly in the short wavelengths or high wave number. And if you put a little bit of the diffusion, so like make it into another Stokes equation, very often they would disappear. These will be killed by the diffusion, even if the diffusion is very small. But on the other hand, the eigenvalues would be much more robust. And the small dissipation or diffusion should not move them too much. This should still produce some instability, exponential instability. If we think about the special problem of the shear flow, then as I mentioned that here, the essential spectrum band has to do with two things. One of them is the Lyapunov exponent of the steady state. And the Lyapunov exponent of the shear flow is 0. So the band, the essential spectrum live on the imaginary axis, and you have some eigenvalues outside the imaginary axis. That's what usually happens. So there have been a lot of previous work on the analysis of the spectrum of the linearized operator of the Euler equation at steady states. So with the linear property, with understanding of the linearized equation at steady states, then a very natural question is, what can we say about the nonlinear property from the linear ones? Usually we expect the linear property should give us at least some indication of the nonlinear dynamics locally near the steady state. That's the whole purpose of doing the linearization, because we want the linear approximation. But again, one has to be very careful with the phase space here. This is the Euler equation is a quasi-linear equation, and it's much more delicate than many of the semi-linear equations. So let's take the Couette flow one more time as an example. So we know that the Couette flow, if we think in the space like LP, it should be considered as linearly stable, and the velocity in the L2 norm even have some decay. There is the linear invasive damping. But if you go to nonlinear, then you see that one could construct traveling waves arbitrarily close to Couette flow in the HS metric if S is not too large. So if you take a reasonably rough norm, but not too rough, then you see that you have the Couette flow, which is a steady state in the, this is a steady state in the family of shear flows, a large family of steady state shear flows. So it's one of them, it's a steady state. And when you take a perturbation linearly in the direction perpendicular to the shear flows, then there should be linear damping, as we saw before. But at the same time, near the Couette flow, arbitrarily close, near the Couette flow, one can find the traveling waves, which are non-shear traveling waves. So it's basically like you have, this is the family of shear flows, and this is the Couette flow. So this line is the family of shear flows. And there always exist perturbations very close. It can be arbitrarily close to the Couette flow. And they are periodic in T. They are not shear flow, they are periodic in T, so they will not decay to the shear flow, to any shear flow. Not only, they are not going to decay in time to the Couette flow, they're not going to decay at all. So you see that non-linearly, there is no damping for in this metric, in the metric of HS, if S is too small, if S is less than 5.5. So the linear invasive damping does not imply the nonlinear invasive damping in this case, in this choice of the metric. But on the other hand, if Chongchun and Masmoudi proved that if you go to the Gevrey class, that's a family, a space of very high regularity, then the linear damping actually holds non-linearly as well. So you see that the regularity of the space does make a difference on the nonlinear dynamics based on the same type of linear dynamics you can see. One of the possible reasons philosophically or conceptually is that if we think about the, the linearization, so why do we use linearization? Because the linearization can be used as a linear approximation for a relatively complicated nonlinear problem. But however, if your function space is too rough, if the function space is too rough, the linearization still, you can compute that formally, but it is not immediately clear that it provides a linear approximation. You cannot really justify the differentiability other than the formal derivation of the linearized equation. So if the linearized problem does not provide reliable linear approximation, then there's reason, so there's no strong reason to believe that the linear property should imply the nonlinear property. So this is something we should keep in mind. So if the regularity is too low, then for these quasi-linear equations, the regularity can be a problem. And this is actually also well known that if you think about a problem like a quasi-linear wave equation, then quasi-linear wave equation is well posed. It has existence uniqueness. But in terms of the continuous dependence or smooth dependence on the initial data, the smooth dependence on the initial data is not in the same function space. You do lose some regularity when you vary the initial data in some Sobolev space and look at the variation of the solution. You can measure the variation of the solution. If you want to consider the C1 dependence on the initial data, then you have to lower the regularity index a little bit in the study of the smooth dependence of on the initial value of a quasi-linear wave equation type situation. So now, then when, of course, eventually we are interested in, or people are interested in nonlinear instability or stability. So a question is, of course, from linear instability, can you obtain nonlinear instability? So this had been a question which was considered for a long time, but the success was really starting in the 90s, I think. But before we do anything, we need to formulate the definition of the instability, nonlinear instability. Well, this is a well-established notion, so what am I talking about? Why am I talking about the definition? So let's review the definition here. A steady state is considered unstable if for any epsilon bigger than 0, there exists a delta bigger than 0, such that there exists a solution which can start arbitrarily close to the steady state, but eventually goes away, at least to the epsilon distance. And so here, the difference between the usual definition we see is that there are two different metric here. Okay. So if you study ODEs in the finite dimensions or consider finite dimensional smooth dynamics, then we'll always just use the same metric because in Rn there is essentially only one topology to work with. But in the infinite dimensions, you have the possibility of choosing two different spaces here. So it's not that we want to make fun and challenge ourselves to make different choice of spaces. This is because we saw that if we take the perturbation in spaces which is too rough, then the linear property may not imply the nonlinear property, because the linear system may not be a good linear approximation for the nonlinear system if this space is chosen too rough. Okay. On the other hand, if you choose this as a function space with too much regularity, then you might get the growth in that norm, which is actually coming from the growth in the very short wavelengths, which is not physically significant. People wouldn't be too much interested in that. So the ideal situation would be to choose the initial perturbation in more regular space with a lot of regularity, with strong regularity, so that you have better property of the system in terms of the finite time dependence. And then you measure the variation of the solution away from the steady state in a rougher norm, so that you catch the growth in the longer wavelengths, which is more physically important. But then this add an extra layer of difficulty in the problem. So it's slightly more challenging. So the previous work, most of the success started in the 90s and starting from 90s. And most of the work were in 2-dimension. And because the 2-dimension had the vorticity formulation, and it can be written, the Euler equation can be written in the vorticity formulation, and then the problem becomes somewhat easier. But if we think about this from a dynamical system point of view, so if we want to show nonlinear instability from linear instability, so here I skipped the part of the linear instability. That's a huge industry of the in the work of Euler equation about the linear and nonlinear instability, like for shear flows. Yesterday, Didier Smets gave some short description of the instability of the shear flows. So I'm mostly skipping that part for now. So assume that you have some linear instability coming from eigenvalues. Okay, that's important, not just from the essential spectrum, coming from eigenvalues. Can you get a nonlinear instability? So suppose that's a distribution of the linearized Euler equation in this picture. And if you look at this, then immediately you see that, okay, the system linearly should be unstable because of the unstable eigenvalues. And from these unstable eigenvalues, I can extract strong unstable subspace, which I called E sub U. So when we have this strong unstable subspace, then if we don't know this is coming from a Euler equation, which is quite complicated, suppose we just think this is from certain nice dynamical system, then I would immediately expect from the experience with ODEs, for example, or some semi-linear PDEs, there should be an unstable manifold or strong unstable manifold associated to this strong unstable subspace. Okay, then what would that do? So that means from this spectrum distribution, you have the unstable subspace given by these isolated strongly unstable eigenvalues. Then you have an unstable subspace which is invariant, where the linear flow has exponential growth or backward exponential decay in time. And the other part of the spectrum will give you the invariant center stable subspace, which is perpendicular, not perpendicular, transversal to the unstable subspace. And intuitively, from the experience with semi-linear dynamics or ODEs, then one should expect unstable manifold in the phase space. So the unstable manifold is tangent to, it contains the steady state. It goes through the steady state, and it's tangent to the unstable subspace. So it's like you have the invariant unstable subspace at the linear level. Then at the nonlinear level, it's still, you can still find something invariant, but you have to bend the invariant unstable subspace into a manifold, so like a surface. Then this is locally invariant. It means that if the initial data start on the unstable manifold, it will follow the unstable manifold. It might go out, but only from the boundary. The unstable manifold is constructed locally. So it's locally invariant. And most importantly, the dynamics on the unstable manifold, which is invariant, is conjugate to the dynamics on the unstable subspace, the linear dynamics on the unstable subspace. So immediately you see some kind of nonlinear instability and exponential growth, in fact. So that's what we said. But at this stage, you see that if I construct the unstable manifold in the function space HK, okay, then I can get the nonlinear instability in the HK metric. So it means that if I take the initial value close enough to the steady state in the HK metric with reasonably large K, and then I will get the growth of the difference in the HK metric. So that's a nonlinear instability within this single metric HK. But at the same time, the major advantage of doing this is that very often we can work with a strong unstable manifold with finite dimension. So if you have the isolated eigenvalues away from the essential spectrum in the previous picture, then your unstable subspace is very often finite dimensional. When this is finite dimensional, then you can, then on this finite dimensional manifold, all the metrics are equivalent. Okay, so on this manifold, even if you take the HK metric, then you get the growth in the L2 distance. So that's what we want in the kind of nonlinear instability. You want a small initial perturbation in a more regular metric, and then you want the growth in a rougher norm, like the L2 norm. So if the unstable manifold we construct in the HK space, even though constructed in the HK space, if it's finite dimensional, then the growth actually happens in the L2 norm. You can make sure that. So that's the kind of desired instability which can be obtained for free if the unstable manifold is finite dimensional. And not only that, it's almost straightforward to get the exponential exit time estimate in the instability because you have kind of conjugacy to the linearized flow. And also, in the usual proof of the nonlinear instability, people rely on the most unstable direction and find the solution growing in the most unstable direction. But with the construction of the unstable manifold, you can find that there are orbits which can grow in some weaker unstable direction, as long as you can separate those unstable directions away from the other spectrum with a spectrum gap. So this gives you a lot of advantage. And also, in the usual proof of the nonlinear instability, people show that according to the definition, for every epsilon, there exists a delta. There exists the epsilon. There exists the epsilon. For any delta, you can find a solution. So that this is true. But if you change this delta, you find another solution. Change this delta, you find another solution. But on the unstable manifold, all the solutions will converge back to the steady state when t goes to -infinity. So any single solution on the unstable manifold will satisfy all the requirement for satisfying the requirement in the definition of the nonlinear instability for any delta. Okay, so any single solution should work for any delta in that definition of nonlinear instability. So this is a stronger result than the nonlinear instability if this can be constructed. And if we think about it, and also it gives you more detailed structure of the local dynamics near the steady state. The experience is that suppose you have spectrum gap, then the construction of this local stable, unstable center manifold should be expected. At least that is the case in the finite dimensional dynamics and in most of the semi-linear dynamics. But there are issues here. But so before we go there, one thing is spectrum mapping. So when we have the spectrum gap in the linearized equation, because we are in the infinite dimensions, so the spectrum mapping is not immediately clear consequence. So you have the spectrum of the linearized equation doesn't mean that immediately you have the growth gap in the linearized flow. That's a so-called exponential dichotomy. So to make the framework simpler at this moment, so let me assume that we do have the exponential dichotomy. So that's a stronger assumption than the spectrum gap. So the assumption is that in our working space, for some Sobolev space HK, in our working space where the divergence-free condition is assumed, non-slip condition is assumed, we assume that this space has a decomposition into the direct sum of the unstable subspace and the center stable subspace. Then not only their direct sum is the whole space, but also we assume that in the unstable subspace, there is a backward exponential decay, but I think I forgot to write lambda u should be bigger than 0. Okay, so this is in the unstable subspace, there is a backward decay. So in the forward time, it grows exponentially. Local, it has the exponential growth in forward time. In the center stable subspace, there is an upper bound. There is the upper bound of the exponential growth. And this upper bound of the exponential growth in the center subspace should be weaker than the exponential lower bound of the exponential growth in the unstable space. That's the exponential dichotomy assumption. But compared to the usual exponential dichotomy assumption, we need to add one more assumption. So this is assumption specifically for the Euler equation we had to add here. That is the gap between the exponential growth rate between the center stable direction and the unstable direction compared to the Lyapunov exponent of the steady flow has to be reasonably large. Okay, this is not an extremely huge number. It's just tedious to compute, but it's determined by the index of the Sobolev space. and the smoothness of the steady flow. And so we want the spectrum gap, no, the growth gap, exponential growth gap in the unstable direction and the center stable direction to be relatively larger than the Lyapunov exponent of the steady flow. And to give an example, if you consider a shear flow, this mu is always 0. So this can be satisfied easily in this case. In other cases, then one need to, if you have like a two-dimensional flow with some saddle point involved, then this Lyapunov exponent is roughly the largest eigenvalue of those fixed point of the ODE given by V star. Okay. And we know that, so here, to satisfy these examples, we can take some unstable shear flow. For the shear flow to be unstable, of course, there should be inflection values. And for example, sine flow for certain beta is definitely unstable, and with Lyapunov exponent of the shear flow equal to 0. So it satisfies all the properties. So these are still mostly standard assumptions for the study of local dynamics. Except this condition is added mainly for the Euler equation, which will be used later. So if we just want to start the usual machinery to construct the unstable manifold for the purpose of proving, partially for the purpose of proving nonlinear instability, then one can start for example, the Lyapunov-Perron framework. One should know that from any elementary graduate ODE course. So if you start the Lyapunov-Perron framework, it really starts with Duhamel's formula. Okay, so you write down your Duhamel's formula. You write first, you take your nonlinear solution and look at the difference of the nonlinear solution and the steady state, and write down the equation for the difference. And the linear part comes from the linear equation, the linearized equation, and there are nonlinear terms. So this is one of the nonlinear terms. And then you write the solution in the Duhamel's principle, the Duhamel's formula, and then you start from here, take the initial condition, some of the initial condition of the unstable component from 0, for example, and the center stable component take the initial the time at infinity, at minus infinity. And then you start the process. That's usually up to Perron process. But there is a problem here. That is, here, this nonlinear term has a derivative, has one order of derivative here. And this one order of derivative in this integral is hit by the exponential operator, the linear evolution operator. But this operator does not have any smoothing effect. It's not like a heat equation or parabolic equation where it has a smoothing effect and can recover the lost regularity in the nonlinear term. Here, it does not happen. So you don't have a clear way how to recover this loss of regularity. Okay, and remember, this L is mainly a transport equation. This transport does not really improve any regularity. So there is an issue here. There is a loss of regularity here. This also has something to do with that it happens actually for some quasi-linear equations, not only for the Euler equation. So how do you compensate this loss of regularity from if you use this formulation? Because this exponential operator doesn't work too well over here. So the first statement we want to make is that, well, it can be overcome, but even though it's not so directly from here, but this issue can be overcome. And assume that the steady state is reasonably smooth, smoother than the Sobolev space we're working in, at least the 4-order smoother. And then we can construct a local unstable manifold. And if we have that the unstable eigenfunctions are also smoother, then we will have some better properties of the unstable manifold, which I'm not going to give here into details. So the bottom line is that this is the main issue to overcome under the assumption of the exponential dichotomy. So linearly, we make enough assumptions. The issue is really the nonlinear term, the loss of derivative in the nonlinear term. How do we overcome that in the construction of the stable and unstable manifold? So by the way, this is slightly more delicate than the well-posedness. In the local well-posedness, if you use this formulation, this issue is still there, but then you don't do that directly. But the construction of the stable unstable manifold is slightly more delicate than that. Essentially, it comes from the smooth dynamical system in finite dimensions in the idea. And as we know that quasi-linear equations like the Euler equations, they do not generate smooth flows. I mean, they do not generate the solution map which depend on the initial data smoothly in the same function space if you are not willing to sacrifice some derivative loss when you compare the initial data and your solution. Okay, so how do we overcome this issue? Then that comes the Lagrangian formulation. So the Lagrangian point of view, as I was trying to advertise from the beginning. So in order to solve this issue, which I'm going to get into more details next time, but roughly the idea is the following. You rewrite the Euler equation on the fixed domain in the Lagrangian coordinates. And in the Lagrangian coordinates, you will find out that it is then your Lagrangian flow map lives in the configuration space, which is not a flat space, but a Lie group of volume preserving maps on the fixed domain. So it's an infinite dimensional Lie group. And when you go to the Lagrangian coordinates and consider the configuration, then it becomes a second order in time differential equation. Okay, second order in time. But the good thing is that when we increase the order in time from first order in the Eulerian formulation of the Euler equation into the second order in time in the Lagrangian formulation, and change the function space from a flat Sobolev space into unpleasant Lie group, we will get a better regularity. And this is pretty much well known, but how do you use that in the analysis? That's something we want to advertise. And then with that better regularity, the problem can be proved to be an ODE on the tangent bundle of this Lie group. So what's the difference between ODE and PDE in the infinite dimensions? A PDE is defined, it's like a vector field, densely defined only, not everywhere smoothly defined, only densely defined. And the ODE is like a smooth vector field defined everywhere. Okay, so this is much better, and many things can be applied. And then, but you pay a lot of price. One thing is to increase the order of in T, and change the phase space into the tangent bundle of a manifold. And also the steady state is not a steady state anymore. It becomes a special orbit of this second order ODE. And then you rewrite the Euler equation near the original steady state. It becomes an equation near a special orbit. Then it becomes non-autonomous equation if you take the principal part from the steady solution. But that's fine. Then we have the exponential trichotomy assumption on the linearized Euler equation in the Eulerian formulation. You can translate that into the exponential dichotomy in for the non-autonomous equation on this tangent bundle of the Lie group. Then use this, you can construct time-dependent unstable integral manifolds. This is some notion well established in, for example, ODEs and semi-linear PDEs. And they are essentially like unstable fibers along a special orbit. Then after you succeed in doing that, then you go back from the Lagrangian coordinate back to the Eulerian coordinate. Then you will get the desired unstable manifold of the steady state. So this is a whole construction we had. This basically says that in order to construct the unstable manifold in the Eulerian formulation, we had this trouble. And to overcome this trouble, we go around to the Lagrangian formulation and do things completely in the Lagrangian formulation, then back to the Eulerian formulation. So it's like really a circle you go around and then come back, except instead of jumping over that difficulty. So in the last few minutes, I'm just going to give you the Lagrangian coordinates, then give more of the discussions on the Lagrangian formulation. But here, when I talk about the Lagrangian formulation, it's not completely Lagrangian coordinates. In many cases, we still do the estimates in the Eulerian coordinates, except we think in the Lagrangian formulation. Okay, so if you start with a solution of the Euler equation, then you can track how the particle moves. Suppose the particle starts at the position y, which we call that the Lagrangian coordinate. Then you track its position at time t. So this is the position of the particle at time t, which started at position y. Okay, so the velocity is given by the velocity at this point. So you solve, if you already have the solution v, you solve this ODE for the Lagrangian flow map. That's U. Then the Lagrangian flow map, because we're talking about incompressible equation, so it must be volume preserving. And also, non-slip boundary condition says that it must map the boundary to the boundary with the smoothness, the same smoothness. Then this is our configuration space for the Euler equation with on a fixed boundary with non-slip boundary condition. And then in this configuration space, immediately we see that these are not linear constraints. These are nonlinear constraints. So it's a nonlinear object. It's a manifold. You can rigorously prove this is indeed a manifold, infinite dimensional manifold, which is a smooth manifold if k is reasonably large, like bigger than half of the dimension plus 1. And then now you establish this is smooth manifold, and it has a group action, of course, the composition is a group action. But here, this is some delicate, there is some delicacy here. The group action is smooth with respect to the left one, but not smooth with respect to the right one when you do the composition. So if you look at phi, composite psi. If you do the variation in phi, you are fine. You still end up with a variation of the composition in the same space HK. But if you do the variation in psi, then it involves the space derivative of phi. Then you lose one derivative. So this is how the Euler equation eventually becomes a PDE. And so for this Lagrangian configuration space, then it's a Lie group. The tangent space is a Lie algebra. That's a tangent space at the identity is a Lie algebra. That's the working space of the Euler equation in the Eulerian formulation. And then the advantage is that this convection term, the transport term, is incorporated into the second order derivative of the Lagrangian flow map. This is well known. So the Euler equation is written in this form. Then the main thing one needs to do is to analyze this pressure term in this form, in the Lagrangian formulation. And it will turn out to be a quite nice thing. But before that, we have to decide a few more things, like what metric to put on this space, on this configuration space. Right now, the differential structure, when I said that this is a smooth infinite dimensional manifold, that is to use the differential structure coming from the HK Sobolev space. Okay, but that's not the best thing you want to use because simply the kinetic energy is not using this metric. But if you want to make sense out of these things, you better have some better regularity. So right now on this page, let's leave with the framework that this is a smooth manifold in the HK space. Okay, but then we have to introduce, and then the equation, the Euler equation is rewritten in this form. So probably, should I stop now?
Yeah, pretty soon you should wrap it up.
Okay, then if I can stop now and then continue next time. It's probably reasonable. If this is the time to stop, then I will continue tomorrow.
Okay, great. Thank you very much. And let's see. So if people have questions, you can ask them in the chat. I've sort of lost track of the chat.
Oh, there's nothing in the chat.
Yeah, there's an administrative question, I guess.
Yeah.
Oh no, that's something else. Okay, so are there any questions for Chongchun? Feel free to unmute your microphone and ask, or else do it via the chat. Okay, so there's one now from Bartek Pratesh. He asks, are there any results concerning the presence of a continuous spectrum?
There had been some results. I assume you are talking about the nonlinear instability related to the continuous spectrum. There had been some results. That's not always true, I think. Check with some results by Zhu Lin, or I think Zhu Lin, he had some result on that. It's not always true.
Okay, well, that may be, so let me thank you for the nice talk, and we look forward to the remaining 2 talks, which is tomorrow afternoon.
Thank you.
And
morning
we'll
afternoon tomorrow.
Yeah, actually I've lost track of the time. It's tomorrow morning, yeah, morning.
Okay.
From 10 to 12, yeah, sorry.
Yeah, I thought it was morning.
Yes, morning's right. Okay, so so Chongchun will resume tomorrow at 10 a.m. And then the rest of us will resume tomorrow. We'll resume at 11 o'clock with the final talk of Jacob Bedrosian. And so we'll be back after a short break for that. Okay.
Thank you.
Thanks. Yep.
Let me stop sharing. How do I stop sharing? Oh, no, it's here. That's why.
Okay.
So Jacob, I've made you a co-host now, so you're able to share your slides.